Which experiences are influential for RL agents? Imagine you've trained a reinforcement learning agent and it performs poorly. Maybe it keeps stumbling, overestimates cue values, or simply learns the wrong strategy. The question you're asking yourself, which experiences in the replay buffer are to blame? That's exactly the topic of today's video. We're looking at the paper, Which Experiences Are Influential for RL Agents? Efficiently Estimating the Influence of Experiences, published in 2025 in the Reinforcement Learning Journal by Hiraoka, Wang, Onishi, and Tsuruoka. The core idea, an algorithm called PIToD, Policy Iteration with Turn-over Dropout, which makes it possible to efficiently estimate the influence of individual experiences on an RL agent's performance. And not just to estimate it, but to selectively disable it. This matters in scenarios like offline RL with mixed quality experience data, safety-critical applications like robotics or autonomous driving, memory-intensive image-based RL setups. Let's dive in. Foundations, Experience, Replay. Before we understand PIToD, we need a shared picture of experience replay. Experience replay is one of the most fundamental concepts in modern off-policy RL. Since DQN, we've known, the agent doesn't just learn from current experiences, it draws on past experiences stored in the replay buffer. In standard policy iteration, two things happen. First, we update the cue function. This is called policy evaluation. Think of it as answering the question, how good is each state-action pair really? The cue function is nudged toward a better estimate of the true return by comparing its current prediction against a target built from the actual reward plus a discounted look ahead. Second, we update the policy. This is called policy improvement. The policy is pushed toward actions that the current cue function rates as most valuable. These two steps alternate, and over time, the agent gets better. So far, so familiar. The problem? Not all experiences in the buffer are equally good. Some come from early chaotic training phases. Some were collected under a near-optimal policy, and some are simply harmful. How do we measure which experience has how much influence on performance? The problem: LOO is too slow. The obvious answer is the leave one out method, or LOO. The idea is simple. Take one experience out of the buffer, retrain the agent from scratch without it, and measure how performance changes. If performance goes up, that experience was hurting the agent. The bigger the change, the bigger the influence. The critical point: in typical RL settings, the buffer grows with every training step. After 1 million iterations, you have roughly 1 million experiences. To measure the influence of each one, you'd need to retrain the agent 1 million times, each retraining taking 1 million steps itself. That's 1 trillion operations. In practice, completely impossible. The paper puts concrete numbers on this. For the humanoid environment at 300 training epochs, LOO would require over 462 days of compute. PIToD handles the same scope in about 1 day. That's the scale of the problem. Now comes the solution. PIToD, Policy Iteration with Turn-over Dropout. PIToD is the paper's answer. The central insight: we don't need to retrain a tool to estimate the influence of an experience. Instead, we use binary masks. Masks and flipped masks. Every experience in the buffer is assigned a randomly initialized binary mask. You can think of it as a unique fingerprint, a long string of zeros and ones, randomly generated and tied permanently to that experience. Alongside this mask, there is its exact opposite, the flipped mask. Every 0 becomes a 1, and every 1 becomes a 0. Here's the key intuition. When the network is trained using experience EI, only the neurons selected by EI's mask are active and updated. The neurons selected by the flipped mask are completely switched off during that update. They never see EI's gradient. They are blind to that experience. This means if you evaluate the network using the flipped mask, you're looking at a part of the network that has never been touched by EI. It behaves as if EI didn't exist. Policy iteration with masks. PIToD modifies the standard training loops to incorporate this masking. During every update, the active part of the Q function and policy is determined by the mask of the current experience being processed. The notation here is important. When you see Q-phi, MI, it means the Q function evaluated using only the neurons that are active under mask MI. All other parameters are zeroed out for that computation, so each experience only updates and is only evaluated by its own dedicated slice of the network. Influence estimation with the flipped mask. Now we can estimate the influence of any experience without retraining. We simply compare two evaluations of the network, once with the flipped mask active, which blocks the influence of that experience, and once with the full network. If the network without EI's influence scores better, that means EI was hurting performance, and its influence score is positive. The bigger that positive number, the more harmful EI was. And all of this can be computed in a single training run without ever touching the training loop again. Implementation details, grouping and macro block dropout. Two practical design decisions make PIToD actually usable in large-scale experiments. First, group masks. The influence of a single experience turns out to be negligibly small, so instead of assigning a unique mask to each individual experience, the authors group 5,000 consecutive experiences together and give them all the same mask. This makes the influence signal much more detectable. Second, macro block dropout. Rather than dropping individual neurons, the network uses an ensemble of 20 small MLPs. Each MLP as a whole is either fully on or fully off, depending on the mask element. This is far more stable during training than parameter-level dropout. Finally, layer normalization is added after every activation, a well-known trick that significantly improves RL learning stability. Theoretical foundation. PIToD is not just an intuitive idea, it comes with a formal proof. The paper proves that the part of the network selected by the flipped mask is genuinely unaffected by the gradients of the experience it belongs to. The argument rests on two assumptions. The first says that each masked Q function slice is dominated by the experience it was trained on, and not much by others. The second says that when a parameter is switched off by a mask during an update, it truly receives no gradient from that update. What follows from these two assumptions is a pair of theorems. Together, they prove that the Y parameters are only ever updated by experiences other than EI. They are mathematically insulated from EI's signal. This gives PIToD its theoretical backbone. The influence estimate isn't just an approximation thrown together heuristically, it follows from provable properties of the masked training process. Evaluation results. The paper evaluates PIToD along two dimensions: how correct are its influence estimates, and how efficient is it compared to LOO. Correctness, self-influence. To measure correctness, the authors use a clever concept, self-influence. Instead of comparing against a ground truth, which would require LOO, they ask a simpler question. Does the influence estimate at least have the right sign? Here's the reasoning. The masked Q function was specifically trained to minimize prediction error on EI. So if you evaluate it on EI, it should score lower error than the flipped mask version, which was never trained on EI. The difference should be positive. Similarly, for policy improvement, the masked policy was trained to maximize the Q value on EI, so it should score higher than the flipped version on that same experience. That difference should be negative. If PIToD's estimates consistently have the correct sign, that's strong evidence the method is working. Results on Mujoko environments: Hopper, Walker 2D, Ant, Humanoid. For policy evaluation, across all 4 environments, more than 90% of experiences have a correctly signed self-influence estimate. That's nearly perfect. For policy improvement, the rate ranges from over 70% in Hopper up to over 90% in Humanoid. Both are far above the random baseline of 50%. There's an important side finding here. Looking at where high self-influence concentrates over time, a clear pattern emerges. Older experiences, those collected at the very beginning of training when the policy was still random, gain disproportionately large influence on the Q function as training progresses. The agent overfits to its earliest, worst experiences. This is the primacy bias, and PIToD makes it directly visible. For policy improvement, this bias is much less pronounced, suggesting the Q function is the main culprit for early experience overfitting. Efficiency. The efficiency difference was already shown in the compute time plot. To summarize, LOO's complexity grows quadratically with the number of training steps, while PIToD's grows linearly. At the scale of the humanoid experiments, this translates to 462 days versus 1 day. Application: fixing underperforming agents. Now to the actual payoff. What do you do once you know which experiences are harmful? The authors show how PIToD can be used to repair underperforming policies and Q functions. The process is straightforward. First, PIToD scores every experience group by its influence on the agent's return or Q estimation bias. Then, the group with the strongest negative influence is identified. Finally, the flipped mask for that group is applied permanently to the network, effectively switching off that group's influence on the final model. The results are striking. In Hopper, the return triples, climbing from roughly 1,000 up to over 3,000 after the amendment. The agent that was failing to hop properly suddenly learns to maintain a stable gait, simply because a handful of early stumbling experiences no longer distort its policy. In Walker 2D, there is also a clear and consistent improvement. For the Q function, the story is equally compelling. In Ant and Humanoid, the Q estimation bias, the gap between what the Q function predicts and the actual return, drops substantially after removing the identified harmful experiences. The authors push this further in 2 additional experiments. First, they test PIToD in DM control environments with adversarial experiences, where 5,000 deliberately poisoned experiences carrying rewards of negative 100 times the true reward are injected mid-training. PIToD flags these adversarial experiences as strongly influential, and the amendment successfully neutralizes their damage. Second, PIToD is shown to work not just with SAC, but also with DROQ and reset, two other popular off-policy agents. Both benefit clearly from the amendment, confirming that PIToD is a general-purpose tool rather than something tailored to one specific algorithm.
3 takeaways.
First, PIToD makes influence estimation in RL computationally feasible, cutting the cost from quadratic all the way down to linear without any retraining. Second, the flipped mask is the elegant core of the method. By training each experience on its own slice of the network and evaluating without that slice, you get a direct proxy for what the world would look like without that experience. Third, the amendment results show a clear practical payoff. Knowing which experiences hurt you, you can fix an underperforming agent quickly and effectively. Open questions remain. How does PIToD scale to much larger networks? Can we handle the combined influence of many experiences at once, not just one group at a time? And what happens in multi-agent or continual learning settings? The paper names all of these as promising directions, and given the elegance of the core idea, there's good reason to expect PIToD will inspire a whole line of follow-up work. If you enjoyed this video, like, comment, subscribe. The link to the paper is in the description. See you next time.